Karthik, were your questions answered in the portal?
One was answered, one was not answered.
Okay.
I don't know. I had asked for working for one of the problems.
Mm-hmm.
They didn't do that.
Okay. Okay, let's start. I don't think anybody else will join. So, in this week, we studied about the application of quantum mechanics to explain some phenomena. Uh, like we used to speak about the discrepancy in the specific heat. So that has sort of been answered in this week's lectures. And how Schrodinger equation is applied to understand the calculate the density of states and other parameters, total number of electrons, total number of states. So the first question is a little bit long, and the rest questions will cover in briefly in a fast fashion. So the first question is density of allowed states for an electron confined in A. A is the dimension in one dimension, angstrom, range, and position total energy of E electron volts will be calculated using which formula? So we'll solve this question in a step-by-step fashion. So we'll start with the Schrodinger equation. The question is clear, right, Karthik?
Yes, sir. Yeah.
Okay.
So option B, I think.
I think uh, it's option B. Yes, you're right. Anyway, we'll solve it. So we'll start from the basics. So first we'll write the Schrodinger equation in one dimension. We write it as so earlier we have discussed that there's no proof for this formula. We have to use it as it is. It was given by Schrodinger. This is only in one dimension, it's the x-axis. And we call this the wave function. And so to apply this, we have earlier discussed that for the potential, if we draw the potential of electrons, so the y-axis is potential, and if we draw it, the x-axis is the position. The potential of an electron, it looks something like this. And here we have the free electrons are contained here. So basically the sample dimension, material dimension. And the bound electrons, these are the ionic cores, and the bound electrons are confined here. So if we take off one of this, if we take one of these potential wells, then we had discussed this question in the previous assignment, that we consider that if this is the potential well, sorry, if this is the potential well, and this dimension is given in the question to be A in it's in angstrom for the bound electrons. We consider that the potential here is 0 and the potential is infinity here. So basically, electrons cannot cross this confinement, cannot cross these barriers at 0 and at A. So inside the confinement,
Sir,
yes, sir. Uh-huh. Yes, Karthik.
I was not able to hear you. That's why.
Okay, am I audible now?
And now it's okay.
Okay, I think there was probably some internet issue. Now it's
Okay.
okay, right?
Yeah, now it's okay.
Okay, so should I repeat any of this, or was it? Uh, this is fine, right? This diagram.
It's
Hello.
fine, sir.
Okay.
Yeah.
Okay. So we can write this equation as d square by dx square of psi of x plus 2me by h cross square psi of x equal to 0. Now we see that we write it as the, what do we write it as? We write it as k square. So k is the wave vector, and this is inside the confinement. Where v equal to 0. Now at the boundaries, okay, so if you would have gone through it, so they say that they take an assumption previously. They say that it's an intelligent guess basically, that a starting point that the wave function should be of the form a cos kx plus b sin kx. This is an assumption, and we see that eventually the solution is in this form only. And so what they do next, we say that at the boundaries, so at this point and at this point, the wave function should go down to 0 because the potentials are infinite. The electron cannot cross the confinement. So psi of 0 is equal to 0. Initially, the cos of 0 is 1, and so A must be 0. So A equal to 0. Since sine of 0 is already 0, so we do not know the value of B. So now we know that the wave function is of the form B sin kx. Then again at the right boundary here, psi of A equal to 0. So what it means is that kx should be a multiple of pi, because on that condition the sine function goes to 0. So kx must, sorry, ka must be equal to n pi. uh, K is equal to n pi by a. You can write the other way also, equal to k by n pi, ka by pi.
K by N.
We will write it as k only, n pi by a. So we see that we have two relations here. So here k square is equal to 2me by h cross square in this case. And again here we have k is equal to n pi by a. So we can put the value of k in this function. We can put this value. And what we get is, if we put it here, what is the value? K of n, then so n square pi square by a square is equal to 2me by h cross square. Okay. So n is 2me a square by h cross square pi square square. So this is the value of n in one dimension. This is important. So now we want to find out what is the total number of states that are occupied, because because it's then from that we can find out the density of states. So basically what we'll do, this is the we'll calculate the total number of states. So if let's say this is the states, this is the energy level. If let's say this is the distribution of states, let it be random, then it can be discretized into small parts. And the small parts can be founded by the differential of the y-axis, which is the density of states. The entire and the total summation area under the curve is the total number of states. So we'll first find out total number of states, and then we will differentiate it, and then find out the density of states. And from that, we can calculate the total number of. Okay, that's what we need to find out: density of states. That is where this question ends. So we'll calculate total number of states. So we say that since it's a infinite sort of a space in n space, so there's a x and y and nz dimensions, and then there is a sphere here. T. So this is the definition of this is total number of states up to energy level. Basically, the total area under the curve. When we differentiate that, we can get the density of state.
That is Fermi energy.
So if it is a Fermi energy, so okay, till now we haven't spoken about the occupation by electrons. We haven't taken Fermi Dirac distribution. So if you have the Fermi Dirac distribution, then you know that okay, at EF there's a hard stop.
Yes.
But the states can be at up to infinite in the infinite space. But that doesn't mean that electrons will be there.
Yes.
So currently we are trying to find out the total number of states in up to energy level E. E can be any value. E can be at less than EF, at EF, higher than EF. So we say that now n is the unit movement. So there are like at unit spacings there are states. So at each of this unit distance, there's a state here in the x-axis, in the y-axis, in the third dimension. So we can say that okay, so each of this space occupies a certain volume, and since it's a unit vector, the state is 1 because that is the unit vector. So we can say that okay, the total number of states in So basically, what the way you can tell total number of states is the volume occupied by all the states in n space. And the unit vectors are nx, ny, nz, and that divided by the volume of each state. Space. Then the argument given is that since n are a quantum number, n is a quantum number, nx, ny, nz, so we can only take the positive values of nx, ny, and nz. So that means nx can be both positive and negative, but we take only the positive direction. So we'll have half for the nx, half for the ny, and half for the nz. We are taking only one part, one direction, only the positive values because they are quantum numbers. And then we can, since we're assuming it to be a sphere, we say the total volume occupied is 4 by 3 pi and cube. And the volume of each state is 1 cross 1 cross 1, because all nx, ny, and nz are unit vectors. So this turns out to be 1 by 8, 4 by 8, 1 by 2, 1 by 2, 1 by 3, 1 by 6, 1 by 6 pi. The value of n can be taken from here, 2me a square h cross square pi square to the power 3 by 2.
Okay.
2me a square by pi square h cross square to the power 3 by 2. This is a cube term, and e to the power 3 by 2. Okay. Now this is the total number of states. Now, as we had discussed, so this is the total area under the curve, or in this case, the area under the surface. And so this nt up to some energy level E is basically the density of states integrated from the origin the energy level E. And so if we want to find out the density of states, we can just directly density of states, we can differentiate by d. This will give us the density of states. So now if we differentiate it, 3 by 2 goes there, 3 1 by 4, 1 by 4, okay, 1 by 4 pi 2m a square h cross square pi square to the power 3 by 2 to e to the power 1 by 2. And this question we are asking for the density of states. Okay, so here it's in terms of Planck constant. So we have to convert h to we will write h by 2 pi, and if we put it here, the density of states will be 1 by 4 pi pi square 8 m a square by h square e to the power 1 by 2. 8 m square. Okay, so this is basically the second option. So this is how we can find out the density of states of a of any material. So this was in the 3 dimension. It can be also done in 2 dimensions or any hypothetical 4th dimension also. The math remains the same in all of these cases.
So in general, value of A, what you had that
This value of a, so
yes,
a is the confinement.
yes,
So there is no in general as such. So in this case, a can be this dimension. So as we discussed, so a can be uh, this dimension. So this will be the density of bound states,
okay,
or you can take this one also. This will be the density of states occupied by the free electrons. So density of states depends on the dimensions. So there is no in general as such. Depends on what dimension you take. For example, if we have let's say you take the nearly free electrons only, but instead of taking a crystal with size in centimeters, you take it as a nanomaterial. Then the dimension will, then this a value will change. Then the value of this a will change, and the density of states will change.
okay.
So it depends on the physical dimension also.
Density means how many number of free electrons are occupied in that particular.
Okay, no. So this is the density of states. Okay, so there is a, this is the density of states. This is the density of, so what it means is that okay, uh, if we draw, this is the number of states, this is the energy. So if you, let's say, move from E1 E2 E plus DE, basically this is the number of DE, then in this range how many states are there? Or if you like in the other way around, if we say that, let's say this is the density of states. So this is the total number of states. The density of states is the derivative of this. So if you take a small region of DE, then how many states are there? And then from this you can find out the how do you find out that, so this doesn't mean that all the that all of these are electrons. So it can go till any distance. On top of this, okay, let us take a more realistic so okay, so let us plot this equation. Okay, since you have, so why take a random one? Let us plot this equation.
It increases with increase in
So we'll plot this equation.
energy.
So density of states, this is the energy. So it goes as this e square root of e. So it will go like this, right?
Yes,
Now on top of this, what we'll do, then we have the Fermi-Dirac distribution, right? So
yes.
let's say we'll again redraw this plot. So in this case, we'll write E, but in this case, the Fermi-Dirac probability. So let's say this is, so this is EF. Then the Fermi-Dirac says it will go at, let's say, we'll draw 2 temperatures. This is at T equal to 0 Kelvin, and then this is at some higher temperatures. So this says the probability of occupation. This is the total number of states, but that doesn't mean all of them are occupied. So how many of them are occupied? So if you want to find out the density of occupied states, it will be this density of states into the probability of occupation, right?
Yes. Into two one factor we consider.
Huh. So then we can again we can redraw this first one. Let's see if I can copy this. Okay. Okay. So then we have to correct this plot, right? And we know that this is the probability. So the correct plot will be something like this. If this is the probability distribution, I shouldn't have. Okay. This is what it will look like. This is the density of the occupied states. This green one. This is at temperature greater than 0 Kelvin, and for at 0 Kelvin, this is the density of occupied states. It will fall down.
Yes.
So that so now this is density of states. Now if you integrate it, what will that be? That will be dE integration from 0 to EF, right? This will be the total number of occupied states.
It's
And then if you now if we say that, okay, now if we say that one state has one electron, for example, then you can just multiply this. Then you can find out the density of electrons, or the total number of electrons, total number of uh, nearly free electrons, because those they determine the conductivity. So we discuss electrons, or let it be like z electrons, which will be z density of states into probability of occupation 0 to EF. So then you can find out the total number of nearly filled electrons, and from that you can predict the values like conductivity and other values. It's clear, right? What is the difference between the density of states, the total number of states, total number of electrons, the Fermi-Dirac probability?
yes, sir. So because last semester, once we studied the basics of the semiconductors,
Mm-hmm.
there we had studied density of states is given by 8 pi root 2 and m by h the whole square whole to the power of 3 by 2 root e. So there this a term was not there in that led to the
Okay,
confusion.
so as you would have seen that this is more like a geometry thing, right? For example, like we took it as a sphere.
Yes.
So if you take it as some other shape, then like we took it 4 by 3 pi r cube.
Yeah.
So if you would have taken it as a cube, then it would have been simply n cube, right? And so so then this factor will change.
Yeah.
So depending on what geometry you take, this value will change. So the point is not to have the exact equation. The more important point is to see the what is the relationship with energy.
Okay.
This exact number doesn't matter. This exact number doesn't matter. So what it should be as a function, it should be a square of the dimension. It should be a square root of the energy. These things matter. Then we can predict that, okay, if the energy increases, then I should see this. If the dimension changes, then I should see this variation.
Yes.
So you need not worry much about the factor of 8 or other values. Okay. Okay, so we'll now cover the rest question a little bit fast because we took the first one slowly. So we have discussed about the Fermi energy, and the next question is what are the typical values of Fermi energy? So in this case, they talk about like in the case of iron.
Yes.
So uh, And if you're wondering like why I'll be discussing about this value, this is basically the KBT at room temperature.
Okay.
So if your system is at room temperature, so is the Fermi level like around that temperature, or like at around that energy, or is it much higher than that?
I didn't get it, sir.
Mm-hmm. Sorry, I didn't understand your question. Did you ask something?
No, no, no. I asked you regarding that KBT
Mm-hmm.
value.
Okay, so I'll first tell you the significance of this question. Okay, because it's more like a fact-based question. I'll
Okay.
explain the significance of this question. So we draw the we draw the Fermi-Dirac distribution, Fermi-Dirac probability. Let's say this is EF. So this is 1, and at some specific temperature, we see something like this. Let it be room temperature, around 25 degrees. So now what happens if you apply now, since it is at room temperature, there's already a thermal energy. This is a thermal energy that exists in the ambient. Like you need not apply any extra energy just because of the temperature of the system. There is an inbuilt energy. So this in this regime of KBT, so in this regime, the electrons can absorb the energy or release the energy in this KBT. Is my clear? So if you remember when we talk about the CV, we say that we apply energy to the system when the temperature increases. So and
Yes.
that we find out. So at a certain temperature, we need not apply external energy. Just because of temperature, there is an energy, which is called the thermal energy.
Yes.
So the question is this the value of EV and the KBT? This value, are they like close, or like this is the value of EV, EF? So what is a so is for iron, is EV approximately close to KBT, or is it like much higher or much lower than this?
Okay. Okay.
So the answer is, so I mean, if you would have seen this plot, so it means that EF is like much larger than KBT from this plot.
Yes.
And so if you see some values, this is from a book called Ashcroft and Mermin. So if you see here, then you can see that the Fermi energy for the case of iron, where is iron?
Yeah. 111.
11.1, huh? This one, right? Where did it go again? 11, huh? So you see, it's much larger than KBT at room temperature.
Yes.
11.1, and it's like for almost all the metals, it is like much higher than at the room temperature. So that is why at the room temperature, only a small number of electrons can absorb and give out energy. Only electrons in this regime can absorb or give out energy. Most
Okay.
of these electrons will remain unaltered. So what it means is that if KBT was in the entire regime, then electron could have come here and they could have jumped here.
Yes.
But since the KT is small, only this electron can jump and come here. This transition cannot take place. I hope the significance is clear.
Yes, sir. But we need to know the table, no, sir. How many values we can remember?
No, no, no. You don't need to remember these values.
Hmm.
As I said, it's more important to understand the scale of stuff. Like
Okay.
exact format. So now you consider, since only this. Okay, since now that this plot is correct, you know that this transition cannot occur, but this can occur. So you can say that only electrons in this shaded region can can absorb energy. So only they will participate in the process of increasing the temperature, which is basically the specific heat. And since a very small number of electrons participate in the process of absorbing energy and increasing temperature, the CV of the material is much lower. Uh,
Yes.
and as we had seen in 2D model, we had 100 times overestimated.
Yes.
And in this case, we see that, okay, where was the overestimation coming from? And more like a qualitative way of uh, explaining it.
Okay. I was thinking of the exam if such a question comes.
No, no, in exam, I don't think you will have questions. Like, I don't think they will ask you value of Fermi energy for any material.
Yeah.
This is not something that people need to remember.
Okay, sir.
There are other values also, Fermi temperature and Fermi velocity.
Yeah.
We'll discuss about it later.
Okay, sir.
So, just to complete it, so Fermi energy is EF. So, you can write it as KBTF. So, and this is the Fermi temperature. Basically, TF, this Fermi temperature is EF by KB. And this is the Fermi velocity, which is basically half mv square, the velocity,
Okay.
which is again energy. You know the Fermi energy, and you know the from that you can calculate the Fermi velocity. So this is again a little bit long question. So the total number of particles which can participate in the process of raising the temperature of a material are which of these values?
It is what the expression of CV what we have derived this.
So from this we go towards the expression of CV, right?
Yeah.
Okay, so
3 by 2 n of PF.
uh, okay, we'll discuss. Let's solve it. I don't have the ready-made solution, so we'll directly take the equations, the solutions from here for dE and the value of total number of states. Okay, so let's write them down here. So the total number of states. Again, I will, for the sake of completion, I will write down the definition of this. Total number of states below the energy level
E.
E. So we found out that the expression for that is 1 by 6 pi 2m a square by h cross square pi square e to the power 3 by 2. And for the density of states, we got the that as 1 by 4 pi 2m a square h cross square pi square to the power 3 by 2 to e to the power 1 by 2. Basically, we differentiated the total number of states E and T and E. This is what we have done here. And so, okay, Okay, there is a power 3 here. So if you take the A out, uh, it becomes A cube. A cube basically the dimension, like x, y, and z dimension. So it's basically the volume. If you take, if you donate it by V. So as we had discussed, so in this question, where is it? Where is the plot? Huh. So in this blue curve, the electrons are occupied only till Fermi energy. The states are occupied only till Fermi energy because of the Fermi-Dirac distribution. So the total number of occupied states, to find that out, okay, and the first we will plot it once. Again, we'll plot the density of occupied states. Basically, dE into the Fermi-Dirac distribution. So that appears something like this. Sharp wall EF. And we had discussed in the previous question that energy levels only in this KT can participate in the process. KBT on the right, KBT on the left. So electrons in only this regime can participate. So we need to find out what is the number of electrons in this regime, total number of particles that can participate. We need to find out what is this regime. This region. How many particles are there in this region? So to do that, we can then write the total number of particles at a total number of occupied states. And since electrons can participate only near EF, electron can participate in the process. So can gain energy as we raise the temperature. And that is in the KBT energy range. So we can write this the total number of states till EF till the Fermi energy. Same expression, we have to just replace E by EF. And we can take it per unit volume. So we'll define this. So this is, and if we consider total number of states unit volume. G. So equal to this becomes equal to if uh, okay, first write it here. NF. What is NF? NF is basically if only one electron per state, then this is total number of free electrons per unit volume. This is clear, right? What I'm doing here.
Yes, sir.
What we are saying is that if each state has one electron, then the density of allowed states is equal to the density of electrons. That is what we have written here, and this can be written in the form we just have to divide NT by.
That's what I was asking in the very first question. What you were, the density of states is equal to the density of. Yeah.
Okay.
Now it's clear. Yeah.
Now it's clear, right?
Yes, sir.
Okay. If the number of electrons per state changes, then there will be a factor here. If it's like 2 electrons per state,
Yes.
then it will be 2 here. And if it's like Z, then Z here.
Yes.
So we have to just divide that by a cube, and it becomes 1 by 6 pi 2m h cross square pi square 3 by 2 e to the power 3 by 2. This is total number of electrons. Now we can if as we had discussed earlier, so this is the total number of electrons, but we do not actually care about the total number of electrons. Okay, so NF, I will delete this later. Let me first draw this. This NF, right? This NF is the total number of electrons in everywhere, this entire integration of the curve. But we don't need that.
Yes.
We need, where do we need? We need only this region, right?
KBT. Yes.
So we will, for that, we can either differentiate this, or we get the same value, or we can, take the density of states and do the same analysis. So we can instead, we can find out this value. We could have just taken this previous equation also, but okay, let's do from the basics. This is the density of allowed states. Per unit volume. Near Fermi energy. So that again we just divide this by a cube. And so if you can directly put it from this, you can correlate this, and you can find that this value. Okay, let us denote. So this is uh, if we write here, okay, so NF, let this be d per unit volume EF. So NF is equal to dVEF into 2 by 3 into EF. Right? Huh? Right?
Yes.
I hope I'm doing right. So basically, the density of states near EF is equal to 3 by 2 NF by EF. And now we have found the density of states, and to calculate the this how many electrons are there, we can just multiply by kBt. So total number of electrons participating.
Yes.
So if the at temperature is equal to T Kelvin, the energy is kBt. So thermal energy. So only electrons. I will just write it down what I had said till now. Only electrons within kBt range around Fermi energy can participate in gaining this energy. This means the kBt energy, and move to the unoccupied state, and like unoccupied the states, it's initially unoccupied. At higher energies. So to find out the total number of particles, you can just say three by two NF by EF into kBt. So okay, so this was the answer, 3 by 2 NF EF kBt. Okay. So I think in the book you'll find standard derivations for this. So, but I wanted you to understand what is happening. I hope you got a little bit understanding of the process.
Yes, sir. Clear.
Okay, thank you. And okay, now we have some smaller questions. So match the following. Which of this material parameter is associated with which property?
Yeah. Temperature is potential for heat to leave the system.
Huh? Uh,
A is 2,
hmm.
B is 1. Pressure, potential for material to leave the system. Yeah.
Yes, and C is 3.
C is 3. Yeah. Potential.
A2, B1, C3. Okay, so option is A. So I just have to say one thing. If all three satisfied, if uh, if all three are in equilibrium, then it's called thermodynamic equilibrium.
Thermodynamic.
If there is no exchange of heat, no exchange of matter, and no exchange of like movement of atoms between of species between phases, then the system is thermodynamic equilibrium. If even one of them is not satisfied, is not in equilibrium, then system is not in thermodynamic equilibrium.
Okay.
So choose the right statements. Fermi energy is a measure of the chemical potential of the electrons. Fermi energy is the product of Boltzmann constants at Fermi temperature. Fermi energy is constant for the system. Fermi surface is defined in K space.
No, 2, 3, and 4. Yeah, but Fermi energy measure of chemical potential.
Huh. So okay, we'll discuss. Uh, so we'll discuss one by one. So let's say first the first option. So chemical potential we know.
Yeah.
So if there are two materials, if there are like two materials and they're in contact, and this is the energy level of electron, the electrons can move here because the chemical potential difference is there.
Yes.
So if we write it in the form of a statement, we can write. Oh, I think it's. I don't think I need to write it. It's okay. I'll write it. When two materials so this is for chemical potential come in contact, if electrons in one of the materials have higher energy, they will tend to flow into the material where they can have lower energy. Right? This is how we define chemical potential. Until when will this happen? Till when? That will happen till the
It's
chemical
balanced.
potentials are equal. Right. So, okay, I should have probably not removed that diagram. So, if we have like electron energy, if there are two materials A and B, so initially this is the electron energy at this level for A, and this is for, if initially it was this for A and this for B, the electrons will jump here. So this will start decreasing and this will keep increasing. And once these two are equal, then there is no more electron transfer. So like equal chemical potentials. Now, when these two are materials are separate, what are these levels? This is the Fermi energies, right?
Okay.
Is it clear?
Yes, sir.
Because what is Fermi energy? Uh, Fermi energy is the
Highest
highest
state
occupied level, right?
at 0 Kelvin. Yes.
Uh-huh. F highest occupied level at 0 Kelvin. So these two are related, right? If a material, if there are two materials, if material A has a higher Fermi energy compared to material B, that means the electrons in the material A are at a higher chemical potential than material B,
Yes.
and so electrons can move from A to B.
Yes.
So this Fermi energy is in fact a measure of the chemical potential of the electrons.
Yes.
Higher Fermi energy, if the Fermi energy is higher, then the chemical potential is also higher. And so statement 1 is correct.
Yes.
Statement 2,
EF is equal to KBT. That's
yes. So this is EF is equal to KB TF, where TF is the
Fermi
Fermi temperature. So this is also correct. Fermi energy is constant for a system. Yes, this is a constant
Yes.
for a system because the total number of electrons and everything,
States.
are, the total number of states, allowed states are there.
System dependent. Yes. It varies from
Yes,
one system.
yes, right. And Fermi energy is defined in K space.
Yeah.
So if we write out, if as we had solved earlier also, we had this equation for, what is the equation for energy? Uh, okay, 2me by h cross square is equal to k square, and this is n pi by a. So if we write the value of E here, h cross square k square by 2m, which is basically n square pi square k square by 2m a square, right? Huh. So we'll write that equation here. E is equal to, and now in all the three dimensions we can write, or actually we do not have, okay, we can simply write this h cross square by 2m. It's written in k space, right?
Yes.
So kx square plus ky square plus kz square. Now this is an equation for a sphere with origin at 0, 0, 0. Origin at 0, 0, 0. For a fixed value of, for e is equal to constant, this is the equation of a sphere. And so it is a sphere in the k space.
Yes. Yes.
We didn't have to go to n square because that would be in n space.
Yeah.
The question is in k space.
K space.
So it's a sphere in n space also, but it's a sphere in k space also. And k is equal to n pi by a. So n is just the dimension is being changed. The unit vector is being changed. So all the four are correct, and so all are correct. Okay, we are short of time, so we'll take 2-3 minutes. I think it should be fine. So the de Broglie's wave particle duality theory plays a key role in understanding the impact of the lattice periodicity inside the material on the behavior of the electrons.
Yes.
Uh, so
True.
we have not discussed this till now, but we will be considering the wave. Actually, we have considered. That's why we are using Schrödinger's equation. But we will be furthermore studying about, we'll use the Bloch theorem to study the anisotropy, to predict the band gaps and all those kinds of properties. So yes, we have to consider the electron as a wave, which is the de Broglie's duality theory.
Yes.
So which of these properties is like determines the crystal structure?
Crystal structure is related to dash position. Ionic core.
Yes, right. Answer is ionic core. So again, if we draw the potential diagram, it looks something like this. This is the potential. This is the position. These are the ionic cores. And the separation between them and the orientation between them determines the lattice parameter and other stuff. comes from this spacing between ionic cores. So the bound electrons are only confined to this location, and so there is no information about the periodicity of the crystal of the ions, and the free electrons are everywhere.
Yes.
And so so free electrons cannot see the position, so they are basically a free electron gas sort of a thing. There is no structure related to that. So free electrons cannot be and bound electrons, both of them cannot determine the crystal structure. Only the ionic cores determine the crystal structure.
Yes.
So again, we have discussed this question in other words in previously.
Equalize, yeah.
Yes, equalize. It's same as that match the following.
Yes.
And the same as that EF and chemical potential question,
Yes.
where we said that EF is representation of the chemical potential of the material. And in our first question, we said that we have a sphere in the n space, but we take on the positive values, right? 1/2 into 1/2 into 1/2, which is basically 1/8. And why is that? Because we take only positive values, right? Okay, I think I myself gave the answer.
Yeah, yes.
The answer is 1/, but I think we had already discussed this question in the first question. Because these quantum numbers nx and nz can have only positive integral values. Okay, I hope there was some addition to your existing knowledge in the class. Okay. You have any questions?
Regarding this, okay, sir. Yeah. No
Okay.
problem. Yeah.
The concept of density of states, the total number of states, number of electrons, there's a difference between all of these values, and I hope you got to understand that.
Yes, sir.
Chalo.
Initially, I had that doubt. Yeah.
Mhm.
It was cleared. Okay, sir.
Okay, if you have any questions, you can ask me in the next class also.
Okay, sir. We can discuss now the assignment questions where for which the data is passed or due date is.
Actually, the teaching assistants should help you with that. I will tell them to have some kind of a solution sheet or something. Let's see.
Till now, for this subject, we haven't provided any this one solution.
Okay, there should be a solution sheet or something.
At least,
Like, do, do you know the solutions of the questions, as in at least which options are correct and all this?
yeah, that they will mention once we due date is over. Every Thursday morning, we get this one.
Okay, okay.
But detailed solutions, why that is correct, that explanation is not there. So in every assignment, one or